good. Okay, awesome. So this is the exam 3 review. We're gonna go over chapters 8, 9, and 10. And my exams are like kind of mixed together. So if you see a question that you guys like haven't seen before, just let me know and we'll skip over it. So let's do question number 1. Let's go ahead and draw the energy diagram. Dr. Dowdy loves energy diagram questions of an endothermic E1 reaction. So let's say that A is this, B is this, C is this, and D is this. What do you guys think?
B.
B.
So I got a couple of answers for B, and that is correct. Actually, before I go any further, I'm going to try and do my breakdown of E1 reactions for you guys and E2. Is that good with you guys?
Yeah.
Okay, awesome, awesome. So that's in one stuff. So let's start a new page. So we have E1 reactions and we have E2. Actually, let's do E2 in a different color. E2 reactions. So E1 reactions are stepwise. So they're going to happen in 2 steps. They have priority for 3 degree. They react with weak nucleophiles / weak bases.
Is it always
if you
only
see-
going to be 2 steps? Or can it be like more than 2 steps?
It's only going to be 2 steps for you guys. I'm not sure if it goes past that, but in Orgo 1, you guys will only see 2 steps or like multi-step. So yes, if you see heat, that's a good indicator that it's going to be an E1 reaction. And then a little bit of a note or like a little helpful tip is that if you have an OH as the leaving group, you'll use H2SO4 and heat as your reagents to get the most substituted product. And over here for E2 reactions, that's going to happen in 1 step. So you react with strong nucleophiles, strong bases. The 1 degree one will have E2 as the minor product. If you have a 2nd degree one, you'll have E2 as the major product. And then if you have a 3 degree, and it's obviously reacting with a strong nucleophile, strong base, then you'll have E2 as the product. And then over here, you would have SN2 as a major, but honestly, Dr. Dowdy doesn't really mix SN2 and E2 kind of stuff. I wouldn't really worry too much about it. But yes, so you can have regio selectivity. I'm pretty sure that's how you pronounce it for these. For these reactions. And you can have Zaitsev, which is going to be the more substituted. Or you can have Hoffman, which is going to be the less substituted. If you have a non-bulky base or nucleophile, then your Zaitsev is going to be your major product, and Hoffman will be your minor. But if you have an actual bulky base, an example is tert butoxide. I know Dr. Dottie really likes that one, and you're going to have Hoffman, which is the less substituted, as your major product, and Zaitsev as your minor. And that's just because when you have something like tert butoxide, it looks like this. So I guess it looks like this. So if you have something like this.
Is what's in black just in general, or is that like supposed to be under E1?
So this is going to be like mostly for E2. For your E2 reaction.
All the stuff written in black?
Yeah, all the stuff written in black.
Well, thank you.
So let's say that you have something like, I'm just going to make X our leaving group. You wouldn't really be able to like put it into there and then have the leaving group leave, right? So, or sorry, I guess it would be attacking the hydrogen. So this would be like our alpha and our beta, but this is like really tight around here. So your tert butoxide won't even be able to fit over there to grab that hydrogen. So it's just going to end up taking the hydrogen from here, forming the double bond, and that will leave. And then you would have a product that looks like this, as opposed to something that looks like that. So this would be your major product, and then this would be your minor product. So that is, let's see if there's anything else that I want to tell you guys about this. I can and then knowing that trans is more stable than cis, and that's pretty much what you guys need to know about E2 reactions. Any questions? Is there any place to find that in the book? Find what in the book, Jordan? Like what specifically?
If you have like the solution manual right before the practice problems in the like back of the chapter, they have like a really good like summary of the chapter that should also sums up like a lot of this. So if that's what you mean, you could like check that out.
Zaitsev and Hoffman parts in the book. It should be in the book. If anybody knows what chapter specifically that's in.
The book doesn't really talk about Hoffman for some reason.
Interesting. Dr. Dowdy's PowerPoints might, if we have time at the end, I can run through his PowerPoints that I have, and we will see. Just leaving stuff. Okay. So we all see why this one is endothermic, because we know that energy is increasing this way. So if it's endothermic, that means that your energy is like entering, and then obviously exothermic energy is exiting. So we know that we're going to have more energy from our product, which means that our product is more unstable, because we know less energy means that it's less stable. And then over here, E1 reaction means that it's going to happen in 2 steps. This one just means that the rate only depends on one thing. So we see our 2 steps here, step 1 and step 2. So then we have our endothermic E1 reaction. Any questions?
Is E1 and SN1 the same energy diagram for endothermic?
They're going to have the same energy diagram, yeah.
And
but like I said, really quick, like I said, he doesn't really mix SN1 and E1 questions. If he does mix it, then it'll be like, I just have like SN1 as an option. Like say that it's like, what type of reaction is this? And it'll be like, let's see, we have like Br over here, and then you have like H2SO4, and that, and then you're going to have this as your product. And then the options would be like A, SN1, B, SN2, C, C1, C, C2. What do you guys think the answer would be?
The E1.
You guys agree?
I'm not really sure how to tell.
Yeah.
I was going by the H2SO4 and heat because that was in the list you just gave us, so I assumed it made it E1.
Yeah, so when you have heat, then that's kind of like a really good indicator that it's going to be an E1 reaction. So obviously, looking at this isn't a substitution reaction, so we can automatically cross out SN1 and SN2, right? So then our options are between E1 and E2. So then over here, because we have heat, it's going to be an E1 reaction. Is everybody good with that?
E2 doesn't require heat.
I can make you guys another chart if you guys want. But honestly, it's pretty much going to be the same thing that I just reiterated. Something also to watch for with E1 reactions is methyl or hydride shift. I'm going to give you guys 2 examples. Let's go back to this page. And then for bases, some examples are, I'm going to do it in yellow. So an example of an E1, that can be something like R, OH2, or H2O. And then an example of a base for E2, that can be something like hydrogen alone, like a hydride ion. I'm pretty sure that's what it's called, for DBN. So those are just 2 examples. And are you guys ready to move on?
Yeah.
Is that OH or was that just a hydrogen?
That's just a hydrogen with like 2 electrons on it. So
Okay.
I think it might be written like NaH as a
Okay.
actual
OH also be one though?
OH.
Yeah.
I feel like OH would be one, yes.
Okay.
Cool. You guys ready to move on?
Yeah.
So let's do this one. So let's do, what is the major product? Dr. Dottie also loves questions like this. And definitely stick around till the end because I have some exciting secret news to tell you guys. I have the following reaction. I forgot to mention that at the beginning. So let's say we have Br and then KOCCH3, 3. So what do you guys know about this? Do you guys know the name for it?
Is it a bulky?
Butoxide, or potassium butoxide.
So this is just writing it out. We have potassium is going to dissociate from it. We have our oxygen, which has a negative sign on it connected to a carbon with 3 methyl groups on it. So this is our tert butoxide. I'm pretty sure it looks like that. I honestly forget how it looks every single time. But yes, what do you guys think is going to happen here?
The major is going to be like the Hoffman.
So the major is going to be the Hoffman. So the first thing I like to do is write where the alpha carbon is so that I can have all of my beta carbons over here. And then the next thing I like to do is write in where I have my hydrogens. So I have hydrogens here. And so where is the least substituted hydrogen? Is it going to be in 1, 2, or 3?
3.
Yeah, awesome. So then we know that we are going to come in with our oxygen, attack this hydrogen. This hydrogen is going to donate its bonds there, and then the bromine is going to leave like that. And this is this an E2 reaction or an E1 reaction?
E1 because it's tertiary alcohol halide.
I think it's E2 because it's a bulky base, and SN
Yeah.
SN is the one that can't do the tertiary, right?
Wait,
why?
So this is going to be E2 because we have our bulky base, but just something that I wrote out during my exams, like at the top of every page, I would write like SN1, like secondary and tertiary, SN2, like primary and secondary, and then E1 and also E2, like secondary and tertiary. But we know that we're going to be doing the least substituted product here because this is a bulky base. So then from this, our answer is going to be this. And this is definitely one of those questions. Wait a minute. Yes. And just make sure that you're paying attention to how things are written, because sometimes maybe if he has the options, actually 1, 2, 3, 4, 5. If he has the options already written for you, it could look something like that, and that's the same thing. I just kind of like moved the isopropyl over. So just like be cautious of stuff like that. And then this is most likely one of those questions where he would have like have the actual like wording for it. So like A would be 2,3 dimethyl hex 1-ene, and he is giving you guys that extra 10 minutes now, so hopefully that will help with getting to write these out.
Is that a Z in the front?
That is a Z. I'm sorry, it looks like a 2.
Wait, what is Z? Is
So
that
we have, what is the other letter? I'm trying to think. It's like when you're doing, yeah, E and Z. So then that's when you're looking at like double bonds and stuff like that. If they're on, if the high priority groups are, so let's say like this is like an OH and this one is also an OH. And then let's say that these are just like hydrogens over here. The way that you would do it is I like to draw a line down the side and say this is the high priority group compared to like between this one and this one. The OH is a higher priority group than this. And then again over here we have OH is a higher priority group than this. So you have Z is the same side. Dr. Dowdy will sometimes tell you guys the ZAME, if that helps you guys remember it. And then E will mean that the highest priority groups are on different sides. So then over here in this example, would they be E or Z?
Z.
Yeah, so they would be Z. So yes, is everybody good with that?
If they're like both the same, like since they're both OH, couldn't you say cis, or is that not? I thought you do the E and Z if they're like different things, or is that not?
So you can pretty much do E and Z because E and Z like encompasses cis and trans within it, but then it's even, it like covers even more things. So like if we're looking at like a circle like this, and we have like the E and Z system of naming, and then over here we would have cis and trans
Okay.
within it, like that. But Dr. Dowdy wouldn't give you like E and then give you like trans,
Okay.
because
Okay.
you know,
Got it. Yeah. Thank
we
you.
know, yeah. But just know that like E doesn't mean the same thing as trans. There are like specific rules for that anyways. So moving on. So then let's say that our last option is 2 isopropyl pent 1 ene. So then drawing these out, this first one looks like this. Second one looks like this. And our last one looks like this. So our answer here is going to be C, 2 isopropyl pent 1 ene. Everybody good with that?
Wait, what was the question again? I'm sorry for this one.
What is a major product of the following reaction? Cool.
Yep. Okay.
Okay, awesome. Let's do the next question. So let's say that we have ranked the following alkyl halides. Alkyl halides in increasing reactivity in an E2 reaction. So let's say that we have this as 1, this one as 2, and this one as 3. So I'll give you guys a second to put your answers in the chat, or if somebody wants to just say it.
What number would be the highest reactivity?
Rank the following alkyl halides in increasing reactivity. Yeah, so like the lowest reactivity would go first. This one is a 2 degree, this one is a 1 degree, and this one is a 3 degree. So I do see an answer in the chat. So we have 1 vote for 213. Do you guys agree?
Yeah.
Yeah.
Okay, awesome, because that is correct. So our reactivity looks like this. I also like to write least reactive and most reactive when I'm doing an exam, just to put everything into perspective, because sometimes as soon as I start putting them in order, I'll like flip it or something like that. So I feel like that really helps me focus what is happening. So yes, are you guys ready for a super fun question now?
Yes.
I swear this is like one of my favorite types of questions. So which, now I promise it's like so fun. I'm gonna be a little bit more enthusiastic. Which carbocation would likely not undergo rearrangement? So we have option number 1, which is this. Option number 2, which is this. Option number 3, which is this. And option number 4, which is this. So okay, so Jordan already knows that the answer is 3. Jordan, do you want to turn your mic on and explain it to us?
Oh, okay.
Or
Okay, so it just, because it's already on a tertiary, or it's already a tertiary carbocation, it can't become more stable, and there's nothing around it that would make it more stable. The other ones go through rearrangements because it's like a secondary carbocation, and it can either like take a hydrogen to shift to being tertiary, or it can take a methyl group.
yeah, awesome. So this can look like this after its rearrangement. Yeah, so it would do like a hydrogen shift. So like the hydrogen from here would now be over here. And then we could have something, the products would now look like this. Or I could say wouldn't look like that. It's okay, we won't write out the products. That's going well, being a little extra. Okay, so then over here we have tertiary like that. Over here we can have a methyl shift. So this methyl right here will end up moving so that we have this. And now we have carbocation like that. So we went from being secondary to tertiary. This is also tertiary. And then over here, let's do the last one. If we were to do a shift, then we could have a hydrogen shift. So let's say that we have one of our hydrogens over here. Then we have this. It's now over here. And then you have your carbocation moves from being secondary to tertiary. But over here, let's say that we are going to have a hydride shift. So one of our hydrogens is moving from over here. Then we have this. The carbocation moves over here. And then we have a new hydrogen over there. But over here, we're moving from being a tertiary carbocation to a secondary carbocation, which means that we are becoming less stable. So that means that this rearrangement won't happen. Rearrangement won't happen. Cool.
Yeah.
Does that
That
make
was
sense to
actually fun.
everybody? I'm telling you guys, pure joy. Okay, let's see this question. Okay. Draw. He actually wouldn't have it say draw, but he would like give you the arrow mechanism. But just for the sake of time, I'm gonna say draw the correct mechanism for the elimination reaction of 2-bromo 2,3-dimethyl butane with methoxide. Let's go ahead and write out what 2-bromo 2,3-dimethyl butane would look like. So how many carbons are in butane?
4.
Yep, 4. And then it's 2,3-dimethyl. So we have 1, 2, 3, 4. We have methyls over there. And then we also have 2-bromo. Let's go ahead and put our Br over here. And then that makes this an alpha. This makes this a beta, and this a beta carbon to get our most substituted product. we are going to react with this hydrogen, and then we are reacting with methoxide. So that's pretty much methyl with an oxygen on it like this. So this is what methoxide looks like. Obviously, he would give it to you in it, but maybe just knowing what it looks like can help you guys. I'm not really sure. But then pretty much what would happen is that our methoxide is going to attack this hydrogen. Bonds are going to be donated over here. Bromine is going to leave like that. And then we are left with our final product of this. And this is one of those like easier questions, I guess, where you guys should just like know how, or he might do something silly like this as an option with like hydrogen and OCH3, where they're like giving their electrons to each other, something like that. So if you just like know that negative goes to positive, so like obviously the bromine is going to be like grabbing those electrons over there, which is giving this carbon here kind of like a partial negative charge on it. You can see where that negative is. So just kind of like remember where electrons are moving, and that can help you guys out. So are you guys ready for the next question?
Yeah.
Okay, so I don't know how I'm going to do on explaining this, but I just want to show you guys the question. What is the major elimination organic product of the following? The following reaction. So let's say we have our nice, beautiful chair conformation like this. And let's say that we have, I think it's deuterium, I believe, which has a higher molecular weight than hydrogen. I think it has an extra neutron. And let's say that we have this. Obviously, the potassium is going to separate itself, so then we end up with something that looks like this. Pretty much what would end up happening is that the oxygen is going to come grab this hydrogen here. The hydrogen is going to go there, and then chlorine is going to leave, and we are left with this product. And you might see other options or things that look like this. I don't have a solid answer for you as to why it attacks hydrogen and not deuterium. If anybody else does, feel free to inform the rest of us.
Do you know why it attacked that specific hydrogen and not the other one?
I also don't have an answer for you for that either.
That's okay.
Yeah, I just don't know.
Wait.
I feel like that was like a
Question.
Yeah, what's up?
No, what was the question she just asked? I just didn't hear.
Why did the oxygen attack that specific hydrogen and not the other hydrogens in the molecule?
I think it's because, isn't it like because it's transaxial to it or something? Because the other one is not like completely opposite, so it's not equatorial. Like that one's equatorial up and the other one's equatorial down. I could be very wrong. That's just a guess, but I think I read something about that in the book. Like about it being like transdiaxial.
Yeah, I think for E2 reactions, it has to be like the opposite.
Yeah, like it had to be like transdiaxial or something like that.
I know that there is a small little snippet in the book about it. I just don't remember what it specifically said in the book. And I remember going into the exam and I like had kind of just like skimmed over it thinking like, oh, it's not going to be that important. And I saw this question and I'm like, what the heck? I thought we were done with share confirmations. But alas, in case it comes up on the exam, just like cover it in the book. And make sure that you guys go over that. So let's see, this one, which set of reagents would be the best choice for the transformation shown? And then we have this. And then we are looking for what reagents might be used. Then we have bromine on a wedge and OH on a dash. We have our options are A, one is Br2, two is NaOH, B is one is Hg, Br2 with H2O, two is NaBH4, C is 1 BH3, 2 Br2, my bad, 3 NaOH, H2O2, and then D is Br2, H2O. So you guys know what the answer could be.
On B, what does it say for 1? Is that Hg?
It is Hg.
What does that mean?
I think it's mercury.
Mercury. That sounds correct. So what do you guys think the answer is? Okay, so we have a vote for D. Does everybody agree with Jordan? I hope you did agree with Jordan because D is the correct answer. Is everybody good with that?
How do you like approach this? Because all of them have like BR and OH, so I'm like, I don't know what to look at, if that makes sense.
Yeah, so you kind of have to just know these. I think these are chapter 9 reactions, if I'm not mistaken. That one is 10. That is interesting because this is not a chapter 10 exam from my recollection. It should just be 8 and 9, 7, 8, and 9.
Ours is 8,
Sorry.
9.
Yeah, I know your guys is 8, 9, and 10. But I think that this, when I took the class, it was 7, 8, 9 that he grouped together. It could be chapter 10 though, I'm not really sure. But there are reactions somewhere in the book, and just pay attention to the regio selectivity, like with the dashes and wedges, because it does come up a lot during this. So yes.
Cool.
It's just like one of those things where you have to just like know it or you don't, kind of. Is everybody good with that?
Yeah.
Okay, awesome. Well, there'll be a lot of these synthesis questions, so I'm just running through the exam that I had, and if you feel like there have been a lot of synthesis questions and that answers it, who really gets to define what a lot of synthesis questions are? All relative. So, okay, wait, I have to see what did you say? Like 3. I think there might be more than 3 synthesis questions. This is kind of where he really gets into all of this. But alas, the show must go on. So let's go ahead and keep going, and let's see if we have more than 3 synthesis questions. We have rank the following compounds in order of increasing stability. So we have 1 is going to be 1 pentene. 2 is going to be E2 pentene. 3 is going to be V2 pentene. And 4 is going to be 2 methyl butene. So you might notice how over here we have butene, and then over here we have 2 pentene. So you can write the number at the beginning before your like parent chain, or you can write it right before the actual ene ending, and this ene ending just means that there's going to be a double bond. So if we're going to write this out, then we have 1 pentene. So let's do 1, 2, 3, 4, 5. That's what that looks like. E, that means that we are going to have them on different priority sides. So then let's go ahead and do 1, 2, 3, 4, 5, 1, 2. Moving that way. Are they trans? Yes, they are. Are they E? So maybe we can break that down. So technically over here we have a hydrogen. Over here we have a hydrogen. So this is our high, this is our low. This is our low, this is our high. So yeah, they are on different sides. So that is our E. Then over here we have the same thing except Z. So we're gonna look like this. So we have 1, 2, 3, 4, 5. 1, 2 is where our double bond is. And if you guys want to check if it's E or Z again, there we have our hydrogens. This is going to be our low. This is our high. This is our low. This is our high. We have lows on the same side, high on the same side. So then that means it's going to be Z. And for our last one over here, we have 2 methyl 2 butene. So bute is 4. So we have 1, 2, 3, and 4, 1, 2, like that, and then 2 methyl, like that. So increasing stability, which one do you guys think is going to be the most stable?
Four.
I got a vote for 4 being the most stable, and that is correct. So this one here is going to be the most stable. Do you guys know which one is going to be the least stable?
1.
I have a vote for 1 being the least stable, and that is correct. So this is the least stable. And then between 2 and 3, which one is more stable?
2.
Yep, so you have second most stable. And this is one of those times where Dr. Dowdy would be nice with the questions, and he wouldn't have you decide between 1 and 3 being the most stable. So he wouldn't give you an option like 1, 3, 2, 4, and then also give you the option of that, because there isn't really a comparison between like 1 and 4. But I guess in this case, the terminal double bond is just like considered more unstable than having it as cis. The reason this is unstable is because of the steric hindrance, and the reason this one is unstable is because it the double bond kind of needs to be like held in place by things, and the hydrogens just like aren't doing a very good job at doing that. But yeah, Dr. Dottie is like really nice with questions like this. And that's why I like him as a professor, because he wouldn't give you these two as options. He would just give you that. And then you would have to choose between like the 2 and the 4 being more stable. So yes, that is the correct answer. Anybody have any questions? Is that a no?
Yep.
Awesome, awesome. So we have our next question. Let's do, what is the product of the following reaction? Is the product. Is this a substitution question? It is. Okay, yeah, so this is going to be not related to this exam, so you guys won't have to worry about it. Make sure you go over the questions in the homework and know how to do the vocab questions. So let's do this one, and I'm going to have you guys name it. So we have BR. Okay, and then we have chlorine over there. Have fun. Unless you guys want to go through it together.
Is this like naming alkenes?
Yeah, so just like name this compound with the correct E and Z designation. So like if he was going to do this and he would say, give the IUPAC name of the following compound, include the correct E and Z designation. And then if you guys finish this one, then you can also do this one.
Have you gone over E and Z yet in class or no?
Yeah, I don't remember it.
Yeah, he
Yeah.
did. He did agree and see.
I think it was Thursday.
I also remember him going over E and Z. So
I remember he was saying like a Russian accent, Z same side. Or he was trying to make fun of like a different country accent, but honestly, I couldn't even tell the difference, not gonna lie.
yeah, I think it's like actually pretty helpful to remember just like Z, same, like a same.
Yeah, Z is Z same side.
Okay, so we have 1, 2, 3, 4, and 5. So we know that this is going to be pent as the parent name. And then from that we have 1 bromo, 5 chloro, 2 methyl, 1 ene. So then putting that all together, our answer for this, oh, and then also let's do E and Z. So this is going to be our higher. Sorry, what?
How did you get 3 chloro? I thought it was 5.
It does say 5 chloro. Sorry, I guess I said 3 chloro, but I wrote 5 chloro. So yes, we can see that our high priority groups are on opposite sides. So we know that this is going to be E. So we have E1 bromo, 5 chloro, 2 methyl, pent, 1 ene. And then for this next one here, we're going to start numbering from here. So we have 1, 2, 3, 4, 5, 6, 7, 8. That means that we are going to have oct. At 4, we have isopropyl. 4 We also have in, 3. We have ol. And then over here, let's put the 1 before the end. Technically you don't, but when I took the exam and then I went and saw the answer key, there was a 1 at the end. So just keep that in mind. So then over here, let's go ahead and figure out in Z. So then over here, we would have a hydrogen. So obviously this is our higher priority group. This is our higher priority group. This one has a carbon, and then this one also has a carbon. This has a carbon connected to an OH and connected to an ethyl, but this has just 2 methyls on it. So that means that this is going to be our higher priority group, and that this is going to be our lower priority group. I think Dowdy said it's better to do that, but both are technically correct, so I would just do it, I think. Yes. So then over here, we have, again, our higher priority groups on opposite sides. So again, we have an E for isopropyl, oct for ene, but you drop the E, put 3 ol. I know that seems super complicated, but it comes with practice. Any questions on this?
Can you re-explain how you found your higher priority groups? Like how do you know where to split it?
So the way that we were doing it for this one, I'm gonna redraw the compound because it looks messy.
You draw compounds so quickly, it takes me forever.
Comes with a full year of doing orgo, so yes, lots of practice. So over here we have a hydrogen, and comparing the hydrogen and the actual carbon chain, obviously the carbon chain is going to have the higher priority group, and then the hydrogen is going to be lower. Did I say the hydrogen is going to have higher? I meant the alkyl chain is going to be higher. Hydrogen is lower, and then from here it gets a little complicated. So we're looking at this carbon. If we move here, then in both directions we have secondary carbons. Like we have like 2 things branching off of it. Mm-hmm. So then from this way we have a methyl, and then from this way we have an ethyl.
Right.
So this one is currently winning by 1 point because ethyl is better than methyl. Mm-hmm. And then from this point we have a methyl, and then from here we have an alcohol. And we know that OH, like having an oxygen connected to something, automatically means that it's going to win. So then that has another point for being a higher priority group. So then that means that this carbon over here is going to be higher, because that's what we're comparing, like this carbon right here. And then this one is going to be lower. So then technically we split the compound down the center like this, and then we compare them like between this one and this one, and we compare this one and this one. So if we have our higher priority groups on opposite sides and our lower priority groups on opposite sides, like they're just like not like this. It doesn't look like this.
So my question is, like, are you always splitting it where the double bond is?
Like splitting it like this?
Yeah, like
splitting it like
it was like split diagonally. You like split it where the double bond was. That's where
I feel like me drawing it diagonally like wasn't the best representation. You split it technically like down here, like where that double bond would be. Okay, so then you're looking at high and high, and low and low. So then this would be same. And then if you had something like I'm gonna erase this one here. You had something like this. Low, high, low, high. Then you have low and high. That means that this would be E.
Okay, perfect.
Does that make sense?
Yeah, I just wasn't sure how to split it to compare the sides.
Yeah, it's okay.
Right, perfect.
So then over here, let's do this next one. And I remember getting this question wrong, and I had never even heard about what ethoxy was in my whole life. So I was like, literally, what is this? Who is she? But it's draw the skeletal structure for the following compound, and we have 2 ethoxy propane. And then let's do R5. I guess this is more of a chapter 9 thing, but I'll write out the question and see if you guys actually want to do it. If not, I'll just give you guys the answer. Dimethyl hexane 3O. So if we have 2 ethoxy propane, so do you guys know how many carbons are in propane?
3.
Yeah, so it's gonna be 3, and the way I remember that, okay, so Jordan says if there were multiple double bonds, you would do it like, I get confused with the way those are written out. Jordan, I am not 100% sure. I would definitely check the book, but if somebody has some advice for Jordan, let us know, because that's not really a question he asked on the exam here. He could, however, ask it on your guys' exam. It would be fair game since it is covered in lecture and in the book. So yes, if anybody knows, let him know. So over here, ethoxy just means that you're going to have an oxygen with like 2 carbon groups on it. Propane, the only reason I ever remember that is like if you have isopropyl, then it'll look like this. And then you can see how there are like 3 carbons on it. So you know that there's going to be 3 carbons here. So you have 1, 1, 2. One, 2, and 3, and then we have 2 ethoxy propane. Okay, give me a second, guys, because I'm pretty sure that the structure I have drawn as my answer is incorrect. So I'm gonna actually Google it and see what 2 ethoxy propane looks like. Ethoxy propane. I don't want to give you guys a wrong answer. Okay, yes, I was doing it correctly. So then we have this. So your 2 ethoxy is like, this is how we're counting it. 1, 2, and then you have your little like oxy part, but then this is your ethyl. So like this is 1, 2, which is ethyl, and then you have propane, which is the parent chain, and then you have 1, 2, 3. The way that you do this is like so extremely strange, because like which way are you numbering it? I don't know. Like that?
If you had a number the other way, would it be wrong? Like if you had 2 on the left side and then 3 on the right side, would that be wrong?
No, that would be correct. So it could also be drawn like this.
Okay.
But because it's the same molecule either way. But yeah, you just like break it down in such a weird way. Like ethoxy is like ethyl with like an oxygen, and then if it's oxy, then you know that there's going to be another chain, and then you put propane, and then it's just 3 carbons. I think it's weird, personally. but who am I to judge? So next one over here, I'm just gonna tell you guys the answer. This is it. ER. Like this, we have our OH. And then from here, we have a methyl that looks like that. Is everybody cool with it? Everybody ready to move on to the next question? I feel like you guys gave me a big head. You were like, oh my gosh, Jenna, you're so good at explaining things. And I'm just like, I honestly don't know what I'm doing. Anyways, I can explain this one for you guys. Yes. So over here we have 3. Oh, so that means we are going to start from. I guess we're starting from this side. So we have 1, 2, 3, 4, 5, and 6. So then over here, you have your oxygen. So I guess you're starting from the left side because you have your OH group on there, and OH has just a higher priority group than Br. That's how it wants us to write it. That like it gave us the text in black, so I'm not allowed to just like flip it. So I have to draw exactly how the words are for this, although I would, if I were naming this, I would name it from the right to the left, just because of the way that the substituents are. But based on what it's asking us to do from here, over here we have our 3 methyl, which is over here our 3-dimethyl, but we also have a 3,5-dimethyl. So we have another one over here, and we have our methyl on the dash because it is the lowest priority group compared to the compared to the ethyl on the side, the OH, and the propyl carbons. And then obviously OH is the highest priority group between that. And then we also have our 5 on our bromine like that. And then if we're going to figure out the R and the S configuration, I like to personally redraw the structure so that I'm able to actually look at it. So then we have 1, 2, 3. This is S. Damn. So actually, I guess the way that I would draw this is just by flipping it, and I would do this. And it makes everything a lot easier if you just actually end up putting the OH on the dash and the methyl on the wedge, because you know what? After you have your S configuration, then you're going to have to end up making it an R configuration. That's how you hack the system. So it would still look like this, 1, 2, and 3. And then we would have S, but because OH is on a dash, we make it R. Everybody good with that?
I'm just confused on why on the left we're using stereochemistry, on the right we're not, and how do I tell like which ones go on a wedge and a dash? I'm just confused on that part.
Yeah, so highest priority goes on the wedge, and then lowest priority goes on the dash. But over here, because the way that I was drawing it before was making it an S configuration, and there isn't a way to draw it without making it. I mean, I'm sure that there is if you like flip it the other way, but my brain just like can't do that. So the simpler thing to do is just flip the lowest priority and the highest priority from being on wedges to being on dashes and vice versa, so that even though it looks like it's S here, technically in reality it's an R configuration. And then over here you wouldn't do stereochemistry because this is not a stereogenic center because there are 2 methyls attached to it. Cool.
Thank
If we
you.
have time at the end, yeah, you guys won't be drawing it by hand anyhow. But if we have time at the end, maybe we can go over more RMS configuration questions if you still have them. But let's move on. Actually, do you guys want to take like a 5-minute break? I'm gonna go play really quick, and then you guys can chat, or maybe I'll leave you guys with this question, and then I'll be back. So it's gonna be draw the skeletal structure of the alkyl halide that forms from the following alkene as the only product of in an elimination product. So pretty much you're gonna want to make sure that you only have one beta carbon to react with. So this is going to be your starting material. That's where it's going to go. And then from that, you want to have this as the product. Good luck figuring this out. I'll be back in like 3 minutes. Okay, anybody have an answer for me?
Would it be like the same pentagon, but with like an ethyl group coming off of that side as the only product?
That is a really good thought. So are you saying that it would look like this?
Yes.
Awesome, awesome. And then over here we would have a halogen. So maybe we would have like a Br or an iodine. So yes, that is what it would look like. If you guys want to know what the like curved arrow mechanism would look like, you could do something like this. So let's say that we have Br over here. So that means this is our alpha carbon, and this is our beta carbon over here. And then from that, we would have our OH like this. And then our hydrogen would be here. The OH would attack the hydrogen. The electrons would move there. Bromine would be there. Can you guys not hear me?
Yeah, we can.
You can? Okay. So then we have our final product. Everybody cool with that?
Mhm.
Okay, awesome, awesome, awesome. So, are you guys ready for another one of those super fun problems?
Yes.
Okay, awesome. So, okay, I'm out of whiteboards to make, so I'm going to go back to this one and I'm going to erase it. Is everybody good with that? Okay, awesome.
Yeah.
So let's do which of the following alkenes will undergo carbocation rearrangement, which will undergo carbocation rearrangement when reacting with H2O in the presence of a small amount of H2SO4. So I'll say that these are our options. Or this. So what are you guys thinking the answer is going to be? I will give you guys, okay, so let's say that our options are A, only one, B, 1 and 2, C, 2 and 3, and D, 1, 2, and 3. So let's say with 1, 3. I'm going to give you guys a hint and say the beta. I'm going to say if beta is more substituted than alpha, then it does rearrangement. Cool. So in this case, we kind of have like 2 beta carbons, I guess, that would be able to react, because we know that we're looking at like what would happen if it were to become a carbocation. So like one of them would still have a hydrogen on it, if that makes sense. So like this would end up looking like this. And this would have like an extra hydrogen. And that's why it's talking about reacting with H2SO4, because if we look at the mechanism for it, then this is what's happening. So we have this, and then you have like H, and then I like to write it as SO4H, and then this double bond, which has electrons, is grabbing the hydrogen, and then this is happening. Does that make sense? Yes.
Yeah.
Why wouldn't both of the carbons be positive? Like, wouldn't both of them have one less?
So because one of them is grabbing this hydrogen. So that's what's happening. So like originally, this one has one hydrogen on it and this one has one hydrogen on it. And now this one only has one hydrogen and this one has two hydrogens. So this carbon is connected to 4 things and this one is only connected to 3, which is why it becomes a carbocation. So if we were to go ahead and draw in our carbocations like this, then it would look like this. So that one will look like that. And we're looking for the most stable carbocation. So I actually am going to write this one out because I'm having trouble picturing what the carbocation would look like in my head. So we had like H2SO4. Then this would happen. So I would go to the oxygen, but like, you know what I mean. And then over here we would have our 2 hydrogens, and then we would get a carbocation that looks like this. And then in the last one, again, we would have to write it out just to see. If I had this question on the exam, I would also write it out. So either way, it's going to kind of be the same thing. So there are 2 ways that this one can react, which can be a sign for you guys. Because we're kind of looking at if this one is going to react, then how stable is it going to be, and can it form pretty much like 2 different beta carbons that can react? Will that change its stability? So from this, I honestly feel like that's one way to approach it, to see like so I feel like this is one way to approach it, but it's not really answering the questions for us. A better way to answer the question for us is this. So over here we have a 2 degree beta carbons, and then over here we also have 2 degree beta carbons. So this carbocation isn't going to be able to do anything because no matter what it does, it's going to end up being 2 degrees. Over here we have a kind of like 0 degree carbocation. It's not really like attached to anything being formed. And then we also have a 2 degree carbocation if it were to form there. But then right next to it, we have a tertiary carbon. So if this tertiary carbon were to donate its hydrogen over there, we would then have a carbocation formed over here. So do you guys think that that one would do rearrangement?
Yes.
Yeah, awesome. So this one would do rearrangement, and then looking at this one over here, we have this one over here is 2 degree, and then over here we have tertiary, over here we have tertiary, and this one is also 2 degrees. So something that can happen is that this hydrogen can be donated over, I'm actually going to put it in red, over there, and then we would end up having a carbocation that looks like this, which is better for it to be a tertiary carbocation and for it to be a secondary carbocation. So is that one going to do rearrangement?
Yeah.
Yes, awesome. So the one that won't do rearrangement is the one that's staying the same because why would the molecule do that? It's just like a hassle on itself for no reason. You know what I mean? So yes, the answer here is going to be C, 2 and 3. I feel like that took me like such a long time to explain it. I apologize. So let's do this one. Okay, I'm going to switch to this page then. Okay, so I'm gonna get to erase for this page.
Yeah.
Yeah.
Don't be sorry, I'm gonna have to rewind and rewash anyways. Okay, awesome. I'm going to clear all my drawings and let's do draw an example of an E2 mechanism. Obviously, this isn't the actual question. The actual question was like a 4 multiple choice one, but I don't have it with me. I only have one of the molecules, so this is going to have to be the way we're changing the question. And yeah, so this is an example of an E2 reaction. So can somebody tell me how many steps an E2 reaction occurs in?
1.
Yep, 1 step. So I'm guessing the rest of the options were happening in 2 steps. Is that good with everybody? Okay.
Wait, what did the original question look like? I don't understand.
So the original question said, which of the following steps could be involved in an E2 mechanism?
Mhm.
And this is what I have
Oh, okay.
as the answer. Maybe I shouldn't have like shown it because I didn't have like the proper question, but just in case it pops up or something like that. So yes, let's do this one. Now we have fun drawing products, which I feel like this is when I started to realize like, oh crap, I'm actually in an organic chemistry class right around this time. So if we were going to do, so the question is just like draw the product, draw the major product of the following reaction. So then let's go ahead and do that. So based on our solvent there, or sorry, our reagent, what kind of reaction do you think this is going to be, E1 or E2?
E1.
Yep, so this is going to be E1, which we know happens in 2 steps. So pretty much what's happening is that our bromine is going to leave as our first step, leaving us with this. And then something that can happen, there are obviously 2 options because we have, this is our alpha carbon, this is the beta carbon, this is a beta carbon, and this is a beta carbon. So then from that, we have hydrogens here, which is the same thing as the other hydrogens. So technically it's like the same product. And then we have hydrogens there. So then from the 2 products that we can actually make, let's attack different carbons, sorry, different hydrogens. And then with this, we have our OH is going to come and attack in different ways. So let's say that our OH is coming to attack this hydrogen like that to do this, or it can come and attack this to do this. Then from our first product, we get this, and from our second product, we get this. So which one is more substituted?
Bottom one.
The bottom one, yes. So our final product for this reaction is going to be this. Any questions on that?
How did you know that it was E1 and not
Just
E2?
Yeah, sorry. So just because of knowing that it is going to, which one do you want to do? Is it strong nucleophile, strong base, or weak nucleophile? I'm checking for you guys. I don't want to tell you guys incorrect information. I'm just like double checking for you guys. It's going to be weak nucleophile, weak bases. So that's going to be something like, literally an example is ROH, and if R is like a carbon chain, or another example is H2O.
He'd have to, I know you said he probably won't give us SN like 1 or 2, but he would specify that it's elimination because it could technically be a substitution as well. Okay.
Yeah, so he would specify like what is the elimination product.
Okay.
Okay, so this is one of like my least favorite questions, and he used to do this for like all of the exams, and I would get like so nervous before them, and they used to be like 12-point questions that were like all fill in the blank, like 4-part question, and if you didn't know how to do that first part, you didn't know how to do any of the question. So you guys can be thankful a little bit that you guys don't have fill in the blank questions like this where you have to draw. But yes, you guys can feel my pain with me alongside, mourn with me. Let's do okay, actually this is working with the same question that we just saw. So this was the first reaction, and the part 1 of the question was saying draw the major product of this reaction. So then we ended up putting this as the answer. And then part 2 is saying what is the rate of the reaction. Of reaction 1. So we decided that this was going to be an E1 reaction. So E1 reactions mean that the rate is going to be dependent upon one thing. So the rate here equals to K times our first little molecule bit. We have the R like that. And we can see that it is on a tertiary leaving group. So E1 is dependent only on the substrate. So this is our substrate. And then provide a detailed mechanism for reaction 1. So detailed mechanism. We went over this, but it looks like this. Br leaves, then we have our tertiary carbocation, and then from there we have our H like this. OH takes that, goes there, and then we have this as our product, and then we have another question. It says, what if we changed the reagent from OH to OK, which is potassium, and keep the other reaction conditions? What will be the mechanism? What do you guys think?
Me too.
2.
Yep, awesome. The answer now would be E2. And that is because we would then have a strong nucleophile. Look at that. She is just dying to give away her electrons. So, yes.
Strong base, right?
So this would be a strong nucleophile, which, yeah, technically would be a strong base if you're looking at the I think it's the Lewis definition that talks about electrons. So bases are things that donate electrons.
Okay, thank you.
Right, so let's do another question. I'm gonna go ahead and clear this. Is everybody good with that? Let's draw a detailed stepwise mechanism of the reaction below. I think I'm going to do one more question after this, and then I'm going to stop the recording so we can go over a couple different questions that I have for you guys. And then we have H2SO4. So pretty much we saw this earlier, how double bonds are kind of like attracted to the HOSO3H, kind of like move where the double bond will grab the hydrogen like that and then give us this and then leave us with, so like the hydrogen will have been there and then we have a carbocation there. Something that can happen here is a 1,2 methyl shift from here so that you can end up getting a methyl shift. I always like to write it at the top just to clarify what's happening because it can look a little bit messy, but now we have a tertiary carbocation, which is awesome for us. And then from here, I'm just redrawing the molecule down here. We can have our water like this come and act as its own nucleophile like that. And then after that, we have this, where we have OH attached to another hydrogen like that. And then we have our OSO4H from earlier that we formed right here. And it has a negative charge on it. Come and attack that hydrogen there and donate that, because we know that water is a good leaving group, but OH is a bad leaving group. So we're trying to make it into a bad leaving group so that we can have a nice content molecule, and this is our answer. Any questions? I always loved reacting things with H2SO4. I don't know why. I had an addiction. So yes. Are you guys ready for some? You're correct. It is a hydride shift. Might be hydride. Awesome. Addicted to acid. I mean, H2SO4 is technically a strong acid, so I could have subtly been making a comment that only true chemists would understand. But alas, are you guys ready for some crack cocaine questions that Dr. Dowdy had as extra credit for these chapters? You guys will cry.
So ready.
Get your Kleenex ready. So let's go ahead and do this. So let's say, which of the following reacts faster? Which reacts faster with HBr? Explain. This was back in the day when he used to do extra credit, but now he just does Alex's assignment so that you can cry not in the lecture hall so he doesn't have to deal with it. And then we have B. Let's go ahead and write our cute little benzene over there. Dun, 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 dun. So just by looking at this, what do you guys think the answer is going to be?
Is it B?
You think it's B? Why do you think that?
It's like a random guess, but I think it's more unstable than A.
It's more oh my gosh. I didn't write the double bond there. My bad, you guys. Are you guys going to change your mind? I'm going to go ahead and give you guys what would happen if they were to react with HBr. So just like this, we would have HBr, double bond would grab the H like that, and then we would get this as a product. We would have, that would be the carbocation for A, and then B, this is what would happen. I am going to draw the benzenes with circles inside so that we don't waste time. And a fun fact, that is a different way that you can draw benzenes, and you guys will learn that when you take Argo 2, which I think is a little bit more fun than Argo 1. Definitely harder, but very fun. So which one forms a more stable carbocation intermediate? What do you guys think?
Is it B?
It is B, because these benzene rings over there are stabilizing, excuse me, those carbons in between. So B is going to react faster than A, because B produces a more stable carbocation intermediate that is stabilized by resonance. You would have had to take a wild guess to get that correct, honestly, because did you guys cover that at all? Not yet. But anyways, are you guys ready for, I think I can squeeze in 2 more questions. I just want to draw these questions out for you guys, and then we can do those last couple questions that I promised. Okay, so let's do the product for these. 1, we have BH3 THF, and then 2, we have H2O2OH. This second one here, we have OH like this, and PBr3, and then the last one here, we have Br on a dash with something like that, and we have H2O and that. I'm just going to go ahead and give you guys the answers to this one. We know that BH3THF, this is going to be anti-Markov. Have you guys gone over Markov and anti-Markov, like Markov-Markov reactions?
I don't think so.
I remember seeing it in the homework though.
Is it chapter 10 material?
Yes.
Okay, yeah, so Markov means that it's going to be more stable, and then anti-Markov means that it's going to be less stable, or sorry, less substituted, I should say. I know there's like 3,000 times where you've heard like how things can be less stable and more stable with like Zaitsev and Hoffman, and now you have Markov and anti-Markov, but Markov and anti-Markov are specifically for reagents. So if you look at, there are like certain ones that are just going to be Markov-Markov and anti-Markov-Markov, and BH3THF is one of those anti-Markov-Markov, because that is, THF is either thermodynamically stable or thermodynamically favored or kinetically favored. I'm pretty sure THF is thermodynamically favored, which means that it needs to have like an ideal temperature and stuff like that. Whereas the one that isn't THF, it's like the other one. I don't remember. So I know that Markov-Markov means that it's more stable, and then anti-Markov-Markov means that it's going to be less like substituted, less stable. But look up the difference between THF and then the other thing that's related to THF. One of them is thermodynamically stable, thermodynamically favored, and then the other one is kinetically favored. And I can't remember off the top of my head right now, but definitely know that before going into the exam. Over here, this is a substitution question, but that's only because there was substitution questions on this exam. But also I think when you guys go over chapter 10 stuff, there are like specific ones for substitution only, if I am not mistaken. And there you go. Those are what the answers would look like. Just in case you guys get questions similar to those, I would definitely look over this type of material. Are you guys ready for the last question?
Can I ask you a question on the OH and PBr3? In the book, it said that those, like, if it reacts with the alcohol, PBr3 only is SN2. So wouldn't it just be the inverted like configuration? Because it says it only does SN2 mechanisms.
And the SN2 results in inversion. Yeah, I guess that wouldn't be SN1, so you wouldn't get an enantiomeric product. Okay, then. I guess we just have the wedge or the dash. Thank you for that. Is everybody good with that? PBr3 is only SN1. Cool.
SN2.
SN2, my bad.
Mm-hmm.
Cool. Okay, awesome. Are you guys ready for another H2SO4 reaction? Yes?
Yeah.
No, maybe
Yeah.
no? Okay. Awesome, awesome. So this is saying draw the major organic product and detailed stepwise mechanism for this. And then you have H2SO4. So pretty much it would look like you have HOSO4H. This is going to go ahead and grab that hydrogen over there so that you're able to make water a better leaving group. Oh, I guess, well, first you have to have your water. And then water is able to leave like that. And then from there,
Wouldn't it be
you have-
OSO3?
I think it would. My bad. OSO3. There you go, because I had already written the oxygen in front of it. But then you have a secondary carbocation, but you are able to do a methyl shift. So you have a 1,2 methyl shift. This time it actually is methyl. And then you get this. So now you have a tertiary carbocation, and then with that tertiary carbocation, you are able to do this. So you have a hydrogen over here, and then the OSO3H that we made earlier over here is able to come grab that hydrogen. Hydrogen is able to donate its electrons just like that. And then we have our final product. Is everybody good with that? Is that an E1 mechanism? So over here, you're reacting it with a strong acid, which means that it is a weak base, which means that I would believe that it would be an E1 reaction, yes. Okay, so I'm gonna go ahead and stop the recording.